All right, good afternoon, everyone. So today we're going to have a really important lecture on what's called the maximum likelihood principle, which is going to be sort of how we think about machine learning, at least the training part for the rest of the semester. It's going to be the way we unify everything. So, sort of as a preview, we're going to learn to understand machine learning as about estimating some statistical parameters in some probabilistic model of our data. So until now, we started really kind of gentle and heuristic. We just said, like, we have a data set, let's apply least squares because that's sort of a good thing to do. But one might ask the question, like, well, when is the least squares the right thing to do? Are there cases where it's not the right thing to do? Are there cases when it is the right thing to do? And this framework helps to understand that. It also helps to explain lasso and ridge and those things, like when are those the right things to do. So the first thing we'll talk about is called maximum likelihood. Then later we'll talk about this second idea of maximum a posteriori. Okay, so in order to explain this stuff, we have to think again in the world of random variables, which we started working with last unit. And so let's just sort of review some basic stuff we also reviewed before. So if I have a random variable y, so I'm making it a capital random variable y just because often that's what's done in probability books. We said that the main way, and we're going to think of this y, this is going to be a continuous random variable. So we said that the way we think about these continuous random variables, like the way that we describe them, is in terms of their PDF. This is essentially, it tells us the density of how often y manifests as different numbers on the real line. And typically, when we visualize these PDFs, the way we think about it is we plot the PDF versus the different possibilities of that random variable. So in this case, we're saying we plot this PDF as a function of y, little y. Y is like just the kind of hypothesized value of the random variable. So as a simple example, say that we have a Gaussian random variable y, and this notation here, I might have described this before, this kind of squiggly line, sorry, I'm not writing clearly, this means distributed as. So we're saying that this random variable y is distributed just like a Gaussian with mean mu and variance sigma squared. Okay, and let's suppose, because we're talking about learning parameters, let's suppose that the mean and the variance are unknown. So we can make different hypotheses about what the mean and variance are. But in any case, what we could do is we could collect those parameters into our theta vector, because theta is typically how we've been writing our unknowns. And we could then have this PDF, py given theta. And because it's a Gaussian with some hypothesized mu and sigma squared, I think you've probably seen this expression before. This is the PDF for a Gaussian. So this is an expression that's going to come up a lot. So yeah, you'll get familiar with it. So here we have y. Here we're subtracting the mean. Then we are squaring that thing. Then we're dividing by the variance, multiplying that by a half, exponentiating it, and so on. And here is a normalization constant. The role of this is to make sure that when you integrate this PDF, that it integrates to 1. That's really what this is doing. Most of the interesting stuff about this particular PDF is in this part, where you can see that it's an exponentiated quadratic. And what this means is that when you plot this PDF versus y, you get this bell curve type shape, okay? And the bell curve is going to be centered at the mean, mu, that we're hypothesizing, and the width is proportional to the standard deviation or the square root of the variance. Okay, so this is typically how we tend to think about PDFs like this. But we have to make a little bit of an adjustment when we think about machine learning, because with machine learning, y is actually a given. We collect y. Y is, let's say, the training we collected. So there's no uncertainty in y. So we don't really want to plot it versus y. The uncertainty is actually in the parameters, in this case, mu and or sigma squared. And so we want to think about those as the three variables, and y is actually fixed. Okay, so that's kind of the leap we need to make. Now, of course, if I just have a single y, I can't really estimate anything from a single value of y. So we need to work with multiple y. So the way that we have been doing this is we say we have samples y1 through yn. We can collect these in a vector boldface y, just to make it a little bit more easier to write. And let's suppose that these are statistically independent samples from some random variable with a PDF P capital Y. And again, there's these unknown parameters theta. These are the things we want to figure out. Someone gives us all this data. From this data, we want to try to estimate perhaps the mean and or the variance. Okay. So this is really the way we're going to start thinking about all our machine learning problems, and I'll show you in a moment how this relates to linear regression. So in doing this, this is sort of a key point. We're thinking about these little yi's, the training data we have, as realizations of some random variables, capital Yi, that are all distributed the same. They're all distributed just like some generating variable capital Y without the subscript. But we're going to assume that all these capital Yi's are independent. It's a slightly more correct way, more easily interpretable way than saying like these samples are independent draws. You just say each one of these came from its own random variable. And when you look at those different random variables, those things are statistically independent of each other, and they're all identically distributed to some common random variable y. Okay, so that's sort of how we're going to think about this. So now we have a whole bunch of data, and we can think about the joint distribution, or let's say, what is the probability now of this vector y? Okay, so this vector y actually has a bunch of samples in it. Each of them corresponds to a particular random variable. So we're really now talking about a joint probability density function that is associated with those capital Y's, but we're sampling it at a very specific spot, which is the data that we received. Okay. Now again, what we don't know, what we'd like to figure out is what are the parameters of that distribution. If it's Gaussian, what is the mean, what's the variance? Yeah, so that's how we're setting it up. And so what's the first thing that I can do? If I have two statistically independent random variables, what happens to their joint PDF? How can I write it? So let's say that I have, that's right. So if I have independent capital A and B, so this is, if they're independent, then I have probability of A, that density times probability of B. So I can write that if they're independent and only if they're independent. So in this case, I actually have n different random variables. They're all independent. So what does that mean about how I can write this joint PDF? Same idea. I can factor it as a product of individual PDFs. So I can write it like this. Product, that's what this big pi means. Product over the indices 1 I equals 1 through n, of the PDF, P sub capital YI, of the little variable little yi, given theta, given my parameters theta. Okay, so this is where the independence comes. Okay, now the way that the independent identically distributed property can simplify things, as rather than saying each of those PDFs has its own random variable, they're actually all identical to this PDF with this common y. Okay. So that is where the identically distributed part comes into play. Okay, is everybody with me so far? Okay, so now this is kind of like the big intellectual leap is we have this function p y given theta. Let's not think about this as a function of y for fixed theta like we did over here. Let's instead think of it as a function of theta for fixed y, because y is the data we have, that's fixed. The thing we don't know is theta, that's our free variables we're trying to learn. This has a particular name. It's called the likelihood function. Okay. And it's sort of an intuitive idea. If you want to find a really good selection of theta, we have this probability distribution that sort of says, like, for a given theta, this is how probable that vector y is. Let's just adjust theta so that we are maximally probable, so that this likelihood is maximized. And that is the maximum likelihood principle. Okay, so this is the main idea. So we're going to work with this. We're going to see several examples, but this is really the core of the idea. And in fact, this is how we're going to do our machine learning for the rest of the semester, is we're going to come up with different ideas of what theta could be, different ideas of what this probability could be, but everything can be formulated in this way eventually. Okay, so that's first main idea. It's a good time to pause for questions. So we collect our data. We have some model of where that data is coming from, this guy. We exploit independence, or we assume independence of the samples we collected. And then we say, what are the thetas that maximize that likelihood function? Those are going to be good thetas for us to use. That's how we're going to learn theta. Okay, I'll show you some examples if this seems too abstract. Okay, any questions before we move on? Yes? Exactly. Yeah. Yeah, so we have these free variables, which are the parameters of our model, which we don't know. But we collected a bunch of data. So let's adjust our model until the data is the most probable thing.
Wouldn't that be similar to minimizing the RSS link over fitting?
Yes, it is very similar. I'll show you exactly how it corresponds to RSS in just a moment. Right. Okay, any other questions? Okay. Great. So, so this is sort of the core idea, just in that box equation there. Now, it turns out when we look at a lot of the probability density functions, just the mathematical form of them, there's often some exponentials and stuff in them. And as a result, rather than working with their raw value, it is simpler to work in the log domain. So it turns out that we can actually rewrite this argmax with log of that likelihood function without changing anything. So the reason why we can just sneak this natural log in there is because the natural log is a monotonically increasing function. So what that means is if you have a bunch of samples and you want to pick the best one, It's the same if you pass all those samples through a monotonically increasing function, because that function will preserve which is the best one. Okay, so that's why you can always sneak in a function here that's monotonically increasing. So now we see, okay, if it's analytically more convenient, we can instead maximize the log likelihood. And that's what we'll typically do. And in fact, we'll make even one more equivalence. We will minimize the negative log likelihood, because that is often the most elegant form of the equations. Minimizing the negative log likelihood. Okay, so that's the idea. We'll see some examples going forward. Okay, any questions before we move on? Okay, so one thing I just want to point out, and we'll get back to this later, is that in doing this, I am making no assumptions about the values of theta itself. Like, maybe I happen to know that theta should be positive. Well, I'm not actually using that here. Or maybe someone tells me, your theta should be close to the value 1. I'm not using that information here. We will use that information later in this other approach called MAP. But right now in maximum likelihood, it ignores that information. In some sense, it's sort of a pure estimate that is not tainted by any prior beliefs. And often if you're doing something like in hard sciences, you're running some experiment, you don't want to have any prior beliefs on the outcome of the experiment, because then you sort of bias your result. So in that sense, this is a really nice way to go if you don't want to make any assumptions about theta. You just want to say, theta can be anything, just find the theta that matches my observations best. Okay, so it's a super powerful approach. Okay, so let's try to visualize what's happening here with a simple example where we have a random variable, y, that is going to be Gaussian, and I'm going to say that the variance is known to be 1, and so the only unknown is the mean of the Gaussian, which we know we have a bell curve, so we don't know where the bell curve is shifted to. It's shifted left or right, it's centered somewhere, it's centered at mu, but we don't know what mu is, so that's the whole goal. So in this case, the parameters, this whole vector of parameters is just simply a scalar mu. Okay, so what do we have now for py given mu? Well, that is just the Gaussian PDF that we saw earlier, except we're going to plug in a fixed variance of 1. So we have 1 over the square root of 2 pi here. And then we have the exponential of minus 1/2 times y minus mu quantity squared. Okay, so this is the form of this generating random variable y. We haven't talked about our data yet. Let's try to make this as simple as possible again. Let's suppose we collect exactly 2 samples, y1 and y2. It's really the, I think it's the simplest possible case to visualize is if we have 2 samples. Okay, so now our likelihood is p vector y given mu, which we know from the previous page. That's like the product of this guy here, but now I'm going to plug in for each term in the product my sample y1 and y2. So I have a product now. There's actually just 2 of them. So I have 2 instead of n. And this is exactly the form that we got from above. Okay. So this is, it looks a little bit, ugly. But, if you had a computer, you could, and you had the data, you collected these 2 values, y1 and y2, you could plug those 2 values in here, and you could compute this likelihood for every hypothesis of mu. So for example, you could make a grid of mu, maybe a dense grid of mu, and you could compute the value of this likelihood over that dense grid, and you would look for a place where it peaks. And wherever it peaks, that's like, okay, that's the most likely value of mu. Okay, so we can actually do this a little bit graphically here. Let's say that the 2 values of, so I'm plotting y again in the horizontal axis. Let's say that the 2 values of y that I collected are exactly those values there and there. So, and I've drawn 3 different hypotheses of what mu can be. Now, really, mu can be any real number, but just I couldn't draw every case, so I drew 3. One hypothesis is mu is -1. Another hypothesis is that mu is 0.2. Yet another one is that mu equals 1. And so what I do in both those cases is I plug in into this expression. I plug in the value of mu that I'm considering as well as the data yi. And so like for this red one, if I'm considering this mu is -1, the two values of this would actually be those two heights of the red dots. So to get my likelihood, I would take the product of those two heights. And that's my likelihood. Okay. Now, if I make this hypothesis that it's 0.2, I get the two green dots. I take the product of their heights, which is quite a bit higher, right? So that has a higher likelihood. Then I have this other hypothesis that mu is 1. I get those dots. I take the product of those heights. I get some other likelihood, right? It's not as high as the green. It's higher than the red. You can see for these 3 different hypotheses, I've computed 3 likelihoods. And you can now imagine doing this for all possible mu. What do you think is going to be the mu that maximizes the likelihood? Just graphically. Any ideas? Yeah.
Where mu is right in the middle of
The green one, right? 0.2. This one? Or you mean a little bit shifted?
or just wherever in the middle of y1, y2.
Yeah. So would that be this green one?
Yeah.
Yeah, exactly. Right. So like, imagine that I consider not this mu, but a mu slightly to the right, larger one. Then what's going to happen is I'm going to have, I'm going to shift my curve over here, and I'm going to have those heights. And the product of those is going to be less than the product of these, right? And if I shift it to the left, I'm going to have those heights, and the product of those is going to be less than the product of these. So really, this is going to be my maximum likelihood. Any shifts in mu are only going to decrease the value of this. And so I've really found it right there. That is the maximum likelihood estimate of mu given those 2 samples. Okay, so the theme here is we have some sort of probabilistic model that's dependent on some parameters. You can think about that as like, a product of PDFs. And as we change our parameters, we're shifting these PDFs around, and we're looking where can I shift them so that when I sample the data, I get the largest value. I get the largest peak. So that's the idea here. Is this sort of making sense now that you see it visually like this? Yeah.
So we are, by looking at the MLE, can we look able to find the variance between the target variables? Or am I?
So all we're doing here is we have some unknown parameters in a statistical model. In this case, mu. We have a bunch of samples from that model, the y's, and we're just asking the question, which parameter explains that data best? So we can actually use this for many things. Like we can use it in machine learning, but we can use it like if you say I have a Gaussian random variable, I don't know the mean, give me a number of samples. It basically says to do the sample mean estimator. That is the maximum likelihood estimator. We'll show that later. It's just sort of a framework to think about estimation. So does it consider variance? No, not really. It's, I mean,
If you have a more spread out data, you said it changes where the MLE is supposed to be.
more spread out data, you mean like the y's? You have more y's?
Yeah, that's something.
Yeah, so definitely like as the y's change, the MLE, the maximum likelihood estimate changes. So if I like start to have a bunch of y's over here, then probably over here is going to be a better fit than this green one, right? So it's just like for this particular set of 2 y's, this mu equals 0.2 was really the right one. Yeah. Okay, so that's, I don't know, hopefully that helps a little bit understand just with an example what we're doing when we, like mechanically, what are we doing when we maximize the likelihood. But this is really how we can now think about a lot of things in the context of machine learning. So any questions on this? Okay, so someone pointed out that it seems similar to what we're doing with RSS minimization, and now I'll show you that yes, in a particular case, it is exactly that. So the question we have now is, can we use maximum likelihood estimation to fit the parameters in linear regression? The answer is yes. So, but what we have to do is we have to be specific about a statistical model. That is something we didn't do in units 1 and 2. We never said that there's a statistical model for our measurements. We just kind of did this heuristic thing and said, oh, there's this error, let's minimize the squared error. Sounds good, but sometimes that's good, sometimes it's actually a bad idea. So now we're going to be a little bit more specific, and we're going to reintroduce, this is exactly the same model we saw many times. We are going to assume that we have standardized data, which means that the intercept term beta 0 equals 0. That means that in this beta vector here, we don't have to include the beta 0 term, and we don't need an A matrix with the first column of 1s. We can just put in our features there. But what we're doing differently here is we're saying that the true model is linear, but with very particular noise values here. What we're saying is that the noise, these epsilon i's, are independent, identically distributed versions of a Gaussian random variable with 0 mean and some variance sigma squared. Okay, we didn't do that before. We're doing that for the first time now. And that is the key to be able to doing maximum likelihood, is now we have a probabilistic model that we can actually apply to this whole procedure and turn the crank and do it. Okay, so what's happening here? If I look at the ith row of y, how could I write the right side of this? So let me ask, and it is Mitchell Leroy here? Okay, what about Josh Lees?
Yeah.
Okay, so Josh, what do you think? Like, this is just a linear algebra thing. How do I write the ith entry of this? So I'll give you a hint. It has to do with the ith row of x. Because we have, this is sort of what we have. This is x, beta is a vector. And so if I look at the ith entry, it involves this row, inner product, this beta vector. Yes, but we need, so I'm going to call xi the row, and then I'm going to put a transpose on it so that it's a row vector. And then I'm going to have the beta vector, yep. And then I need one more thing here, the last part, plus epsilon I, right? Looking at the ith version. Okay, so what I'm trying to do is walk you through something that you'll have to do over and over again on homeworks and maybe tests too, is, okay, so now we can clearly see the ith measurement has this form. This is just a scalar. It's a row times a column. And then here we have another scalar. And we said this is Gaussian with mean 0 and unit variance, or sigma squared variance. Okay, so here's the question. What is the probability model on yi? First of all, like, yi is what kind of a random variable? Is it, it comes from some family of random variables, some distribution. What is that distribution? So we know these guys are Gaussian. Okay. We are going to think of it about x and beta just deterministically. Those are not random at this point because we're conditioning on them. So this is not random. Okay, so if this is if this is Gaussian and this is fixed, what is their sum? Gaussian, exactly. What is the mean of that Gaussian? So what was the mean of the epsilon?
0.
0, okay. So if I have a 0 mean and I add a constant to it, what does the mean of this new random variable become? That constant. And what is that constant? Xi transpose beta. Okay. And then does the variance change because I added this constant? Doesn't change. So I have this new random variable y, which has a mean of this and the same variance as before. Okay, so this is like a key step. This appears over and over again. This is really important to know. Sometimes, like, this is sort of the gateway to doing the rest of the test problem, is if you can't get through the first step to set it up, you can't do anything more. So this is super important to understand this little thing right here. I'll put a star by it. Okay, so now what's good about this is we are ready to do maximum likelihood estimation. We have exactly what we need, which is this distribution, this scalar random variable. It's just Gaussian with a particular mean and a particular variance. Okay, so our likelihood function, which is this. So here, beta are the unknown parameters that we want to adjust. X, we're just treating X right now as some fixed thing we know. We're gonna think about it as maybe random, but we're conditioning on it, so it becomes this fixed thing. Okay, and we said that, okay, if I fixed my data and this, then the only thing random left are the epsilons and their IID. That means that this joint distribution, this factors into a product of what we call marginal distributions, these scalar ones. Okay, so this is always the first step of maximum likelihood. Write the joint as a product of these marginals. Second step, plug in what we know about this. Well, we know that that is exactly this. And so now I'm just writing the same thing, but in its mathematical form. Here you can see the mean. Here you can see the variance appearing there and there. Okay, just the standard form of that Gaussian. Okay, is everybody with me so far? Okay, so now we get to do some gymnastics that we do over and over again with these types of problems. So it uses this important idea. If you have a product of exponentials, let's say e to the a times e to the b times e to the c, is there a slightly easier way to write this? What is it? Does anybody? Exactly. It's e to the a plus b plus c. Okay, so let's apply that idea. Here, we have a product of these things. Okay, great. So we can take this to the nth power. That gives us this. More interestingly, we have a product of these exponentials. Okay, that means we can, instead of it writing that as a product, write that as a sum inside the exponential. So it's just exactly doing this. So here I have moved that product inside the exponential as a sum. Is everybody good at that step? Okay, that's a step you'll see over and over again. The last thing is, let's tidy this up, and instead of writing this quantity here as a sum of squared things, we know that that's actually the norm of the vector that we can create from this. This is actually the ith element of a particular vector, which we saw before as y minus x beta. So let's just put that inside a norm. Okay, so now we have a really concise way to write our likelihood function like this. And now you can see that this is still a little bit messy, and that is why we want to use the negative log to, again, tidy things up. So let's see what happens when I take the log of this. So here, if I take the log of a divided by b, what is that? Log of a minus log of b, right? Exactly. So we're going to use that quite a bit. So when I take the log of this, I get the log of the top. That log kills the exponential part. I get this. And then I get minus the log of the bottom, which is this. Okay? Now, I'm minimizing this thing over beta, so this log of the bottom has no betas in it, so this is not going to affect my minimization. So in fact, we can forget about it. And then the other thing I mentioned, the log killed this. The negative sign kills this. And so all we have left is arg min beta of 1 over 2 sigma squared times that norm squared. Starting to look more and more like linear regression as we formulated it before, right? Can I make this even simpler? Is there something I can simplify about this? So we're saying, what is the beta? We're trying to figure out the beta that minimizes this. Does this part play any role? No, right? This just scales the entire thing. So if I find the beta that minimizes that, it also minimizes this. So actually, I can write this as argmin beta over y minus x beta, quantity squared. Okay, and now we are doing least squares. So we have recovered least squares. We're explaining when least squares is a great thing to do. So what was the key assumption that allowed us to show that maximum likelihood becomes least squares? What was the big assumption we made? Exactly, that the noise was Gaussian. So when the noise is Gaussian, least squares works great. In some sense, it's optimal. It's optimal in the sense of maximum likelihood. When the noise is non-Gaussian, least squares may or may not be a good thing to do. Certainly, it is not justified by this when you have non-Gaussian noise. And in practice, if you have noise that has what are called outliers, so once in a while, there's epsilons that are really large, positive or negative, really large, really far from the mean. Least squares gives you terrible results. It breaks down. It's not robust to outliers in the data. So if you have if someone collected a data set and there's just a few values that someone typed in wrong into a table, they're completely off, that will really mess with least squares. And there's much more robust approaches to least squares, and how you can get them is you can assume a different statistical model that has heavier tails than the Gaussian model. So the statistical model says, yeah, I expect to have a bunch of large values once in a while. You derive maximum likelihood under that, and you get a much more robust approach. One example of that is what's called L1 estimation, where you actually, instead of minimizing the Euclidean norm, you minimize the Laplacian, you minimize the L1 norm. And the way that you get that is that you assume a Laplacian distribution on the noise. That's much more robust to outliers. Okay, that's a little bit aside, but the key point here is that if we make this key assumption, we do maximum likelihood, we recover least squares as we derived it heuristically in unit 2. So that's a big concept. All right, great time for questions. Is this sort of making sense?
So when you're talking about outliers, if there was a very small percentage of those outliers compared to other statistical data, can you just not prune them out and just fit it into the Gaussian and still make it work?
Yeah. So it turns out there's different ways to handle it, and depending on the statistical assumptions you use, you can recover these kind of pruning estimators as statistically optimum under certain assumptions, either on, the way that the epsilons are generated, or as we'll talk a little bit later, where the betas are coming from. So you can recover all these special cases, not all of them, but a lot of them, as they're optimal under certain statistical assumptions. So it's a really good way to, when you propose something, you actually feel good. You're like, yeah, I'm just not making this up. This is actually the right thing to do in this case.
You mentioned that MLE was optimal. Wouldn't you need a large enough sample size to justify the IID assumption?
Yeah, so we would need to do more work to show exactly when the maximum likelihood estimator is optimal, but we're just going to kind of take it. We're not going to do that in this course, but we're going to think about it as sort of a good thing to do in most cases. Okay, great. So any other questions on this? Okay, so now we're going to take this in a slightly different direction, and we're going to say, well, what if in addition to this statistical model that I have that relates, the betas and the x's to the y's, I have some additional information. Someone tells me, they give me a hint about what the beta should be. So I have some prior belief. Maybe the hint is like, your beta should be really close to 0 in some sense. That should affect me. If I capitalize on that information, maybe I'm not going to do this anymore. Maybe I'm going to do something a little differently. So that is the idea behind maximum a posteriori estimation, or MAP estimation. So the way that this is defined looks like this. Okay, so the key difference between this formulation and maximum likelihood is that when we did maximum likelihood, the y's were on the left of the conditioning and the betas were on the right. Now somehow they get swapped. So the interpretation here is a little different. In fact, it's even a little bit easier. The interpretation says, find the most probable beta given the data x and y. Right? It's actually, in some sense, easier than maximum likelihood, where you have to do this mental gymnastics to figure out, okay, what are we actually doing? Here, we're just saying, if you give me this data, that induces some sort of distribution on beta. Let's just find the beta that is the most probable. This tells you what is the probability of different betas under this data here. Okay, so in some sense, this is just makes more sense. But as we'll see, this requires one additional thing. It requires this information about beta, which we may or may not have. If we don't have it, we just can't do this. But if we do have it and we feel comfortable exploiting it, this can really help us. Okay, so any questions at the high level of MAP? Okay, so the key thing is now we have additional information about beta. Okay, so the way that we use this is we use an important relationship called Bayes' rule. So let me first write it maybe in a simpler way. So if you have two random variables, b and a, and you have this conditional probability b given a, and for whatever reason, that's hard to formulate, but a given b is easy to formulate, there's a way to kind of swap the order of the conditioning, and that's what Bayes' rule does. You get a probability of a given b times probability of b divided by probability of a. Okay, and so this is useful when you know all of these things, but you don't know this thing. This allows you to figure out this thing from what you know. And as I'll show you, that is exactly what's going to be the case for us. We know these things on the right, but we don't know this thing on the left. This one. Okay, so now one slight complication, maybe it's in the notation mainly, but I want to explain here is that the two things we want to swap here are really the beta and the y. We want to swap those on the side of the conditioning. This x, we're just going to leave it on the right in all cases. It's always just going to be this condition on x. So in order to change up Bayes' rule, all we need to do is put an x on the right everywhere. So condition on x everywhere here, and then we can still write Bayes' rule. So let me write it out here. So we have in the numerator py given beta and x times probability density of beta given x, and then on the bottom probability y given x. Okay, so all I did to go from this sort of simple form to here is I just put a conditioning on x everywhere. Okay, that's it. And it still holds. Okay, so now when we look at this, we can recognize some things. So this guy is exactly our likelihood. This is what we were working with before. So we know this. Like for the linear Gaussian model, we already derived exactly the form that takes. Okay, what about this term? Okay, so first of all, we're saying, what is our prior belief about beta given the training features? Well, if we have a prior belief about beta, it doesn't really involve the training features. It's actually something, by prior, it means like some belief you have before you collect any data whatsoever. So what that means is that this we can rewrite this without that conditioning on x on the right. So it's just probability of beta. Okay, so this is going to be our belief about beta. We're going to say beta is a random vector and it's generated by this distribution. And so we have to come up with some sort of choice of what that distribution is, or someone gives us a hint as to what that is. Yes?
What happens if our prior belief is wrong?
Prior belief is wrong. This method can backfire on you. Can give you a bad answer. Yeah. So this is something we use, only when we trust it, or maybe we use it to explain. I'll show you how this can be used to explain ridge and lasso. It's kind of equivalent to trusting something about beta. Okay. And then in the numerator, we still have this term, Py given x. But what I want to point out about this numerator is that, our goal is really maximizing beta. Okay. Beta shows up in the likelihood, it shows up in the prior. Beta does not show up in this denominator here. So if I want to maximize this, I actually don't really care about this part. It doesn't really affect my maximization. I really just need to worry about what happens in the numerator. So finally, down here I get arg max over beta of this product P, y, given beta and x, the likelihood, times P of beta, which is my prior. Okay, so the difference between maximum likelihood and this, maximum likelihood, this prior term is not there. Now, the prior term is not there. Now, with map estimation, the prior term is there. Okay, so there's really two things we're trying to do simultaneously with map. We're trying to find parameters, beta, that agree with the data as given by the likelihood. We're also trying to find parameters, beta, that agree with our prior beliefs about what beta should be. Okay, so map estimation uses both the likelihood and prior, whereas maximum likelihood is similar, but no prior information used or needed. Okay, so that's another nice thing. Maximum likelihood, you don't have to make any assumptions. Here you do. Okay, so that is basically, that's map. Any questions about how it's formulated? Yes.
Can you state one more time why the beta vector is independent of that vector?
Well, I guess it's maybe you could even say it's sort of a modeling assumption, but we're saying, I guess here's one way to think about it. Like, if you gave me features and targets together, I could make sense of what beta is. If you give me one or the other without its complement, I can't, right? So maybe that's one way to think about it. Think about this assumption. Given the features alone, I can't really tell you what beta is. Given features and targets, yes. But features alone, I can't tell you. Okay, great. So any questions on this? All right, so let's now think about how this relates to linear regression. Okay, so just as we did with maximum likelihood, we could instead work in the log domain. So here we're maximizing the product of these two. We can sneak in a log of the product. That won't change anything. We can even sneak in a negative log if we change the max to a min. So that's what we've done here. Snuck in a negative log, changing max to min. And now we can use the fact that the log of A times B is the log of A plus the log of B. So we get this separation. Here we have our negative log likelihood. Here we have this new term, the negative log prior. Okay, so what happens with our linear Gaussian model? So the linear part of this is here. The Gaussian part describes our assumption about the noise epsilon. So we saw a couple pages back, this negative log likelihood is 1 over 2 sigma squared times this Euclidean norm squared y minus x beta squared like this. And then we had one other term, which was a constant with respect to beta. So the constant with respect to beta, when we did maximum likelihood or minimizing the negative log likelihood, we basically just ignored it because we knew it doesn't affect how we choose beta. Okay, so I'm writing it here just for completeness. It is there, but the details of it are not important. Okay, so now plugging this into here, because we're doing a minimization over beta, we can ignore this. That doesn't change the arg min. So we get arg min over beta of 1 over 2 sigma squared y minus x beta norm squared minus the natural log of p beta. Okay, so here we have our negative log likelihood. Here we have this other term. And to make this look identical to our regularized least squares estimation, we're just going to move this to the other side. Essentially, we're going to minimize 2 times sigma squared of this whole thing. So that will cancel this, but it will appear over here. So that's arg min beta of y minus x beta quantity squared minus 2 sigma squared natural log p beta. So this, on the left, we recognize this is exactly RSS. And this other stuff here, we gave that a name in the sense of, in the context of regularization, we call that phi of beta. Okay, so basically, we now have regularized linear regression. RSS plus some other term, depends on beta, that influences how we choose beta beyond just minimizing RSS. Okay, we can actually notice sort of an interesting thing here. So as my measurements become less and less noisy, more and more clean, they're more and more powerful, right? Like, if you tell me this is the measurement and there's almost no noise here, you got to believe those measurements. So as sigma squared gets small, it automatically downweights your prior belief. Basically, your prior doesn't matter as much when the noise is really clean because you got to pay attention to those measurements. Those are telling you the truth. Your prior kind of should ignore that and focus more on these. So it's kind of visible in this term here. Okay. All right, any questions on this? Okay, so we're almost done then. This is what we have from the previous page. And now let's look at a couple examples. What if our prior belief is that these beta j terms are close to 0 in the sense of being drawn from a Gaussian with a mean of 0 and some variance v? The smaller that variance is, the more confident we are that the beta j's are close to 0. As that variance increases, well, they're centered at 0, but they could span a pretty wide range. So in this case, if that is the assumption on these beta j's, they're IID Gaussian mean 0 variance v, we can write the joint PDF of them as the product of these individual Gaussian PDFs. These are with the mean 0, variance v. And then when we take the log, as we want to do here, we know that turns this the product into a sum Actually, we're going to take the negative log, so that's, actually, no, sorry, this is just the log. So we get this term here plus a constant. So it's the 2 norm of beta squared, and then we plug this back into here. We can ignore the constant because we're minimizing over beta, and we get exactly this ridge regression regularization term, but now with a very specific weight alpha. And that weight is the ratio of the noise in the measurements, the noise variance in the measurements, to the belief, the variance in our belief of beta. So they're sort of calibrating each other. The alpha gets smaller as we get more precise measurements, but alpha gets larger as we have a more precise belief. Okay, so it's sort of calibrating alpha directly. The other example is, what if these betas are from a Laplacian distribution? The Laplacian distribution is kind of like a Gaussian, except it's missing the square. It has an absolute value here. And instead of a variance, it has a scale parameter lambda, which determines its width. And it turns out that here, if you take the log of this, you get a sum of these absolute values, which is the L1 term. You plug this in, and you get the lasso regularization. So this is like saying you have a prior belief that the betas are centered at 0, but once in a while they can be quite big. And it turns out that when you do this, you get exactly lasso. Okay, so it's just kind of connecting back like where these things come from. There are statistical interpretations, and that's often the case for estimators that work well. There's some statistical model under which that's the right thing to do. Okay, great. So we're almost done then. Any questions on this? All right. So just very quickly, what we said, the maximum likelihood estimate is argmin over theta of the negative log likelihood. No prior belief. Map is the argmin of negative log likelihood minus the log of the prior belief. And the latter has a belief, the former no prior belief. Okay, so one last thing I want to cover because it's useful for the lab, in case anyone wants to start the lab over the weekend. So it's not a very big idea, but it's how do you go from scalar value target to vector value targets? So until now, our targets have all been scalars, yi. What if instead of predicting one thing, I'm predicting actually several things simultaneously from the same features? So now what we have, let's say we have k of these things we're predicting, k targets. So for the ith data sample, I now have a vector instead of a scalar. So that vector has k different things in it, the k targets I'm predicting. So think about that as boldface yi transpose. The features are identical. In order to predict these different things, we're going to use different beta vectors. The beta 1, the first beta vector predicts the first target, the second target, the kth target, and so on. So that's really the generalization. We have several beta vectors, several targets. We can stack these samples as rows in a matrix. We end up getting a y matrix instead of a y vector. The A matrix from before, that's identical. And then we just stack these column vectors, these betas, into a matrix we'll call B. There's no capital beta, so just call it B. So we just have matrix Y approximately equal to matrix A times matrix B. Okay, so this is the model that's used in the lab. So it's useful to know about this. And it turns out the nice thing is all the sklearn software, it scales I mean, it just handles this seamlessly without any issues at all. You just, you give it a Y matrix instead of a Y vector. It just knows to estimate a bunch of different betas and so on. The only last thing to talk about is really notational. So this is the new model in terms of matrix Y, matrix noise. Here we're going to assume that all the different epsilons in here, they're all independent, zero mean, sigma squared, Gaussian. So now, if you did maximum likelihood, you would want to minimize this. So the one thing I want to point out here is this little subscript f. This is what's called the Frobenius norm of a matrix. So if you have a matrix, and what you want to do is you just want to sum over all of its squared values, this is called the squared Frobenius norm. If you wrote a 2 down there, or you didn't write anything down there, you would have a very different norm, which is called the operator norm. Behaves totally differently. It's the maximum singular vector of the matrix. It's a singular value. It's not at all what we want to do. We want the norm, which is the sum of the squares of the matrix elements. And so that's just notationally, and if you code this, you want to use a Frobenius norm. So what we have is the Frobenius norm there, as well as in our ridge regression, our ridge penalty. Now, if we're talking about lasso, we know we want an L1 norm. It turns out the L1 for a matrix and the L1 for a vector have the same notation. So if you have a matrix, you want to sum the absolute values of the coefficients. That is the matrix L1 norm. You can write it as always with just the 1 on a matrix. But with the 2, it's different. Okay, so that's really all I wanted to say. It's more of a notational thing than anything. But with that, you're good to start working on your lab if you wanted to do that this weekend. All right. Sorry I went a little bit over time again. Hope you guys have a good weekend, and we'll see you on Monday.